So hello everyone, and welcome. I hope you had a good lunch. We'll start this second session with Ian Eisenman, who's going to talk about two Antarctic sea ice enigmas and proposed explanation.
Thank you, Noah. Okay, this is on, I can hear it. Many thanks, Jordan Pitt, and the other organizers for putting together a fantastic meeting and also for inviting me to participate in it. So before I dive in, I want to say, I hope everyone will feel free to interrupt me along the way with any questions, comments, or complaints, if that's okay with the organizers. I'm going to be talking about two enigmas. You get two enigmas here for the price of one. The talk will have two parts then, and the first part of this talk is research that was led by Letty Roach, who's been mentioned already this meeting, and she's a NOAA Climate and Global Change postdoctoral research fellow in my group right now. And then the second part of the talk will be on research. I'm just moving this to the side. Okay, there's a mouse there, but it's not mine. Anyway, the second part will be research that was done by, is a thesis chapter of Shantong Sun, who recently completed his PhD in my group. And several of my colleagues have also contributed to some of the work I'll present, including Cecilia Bitz. So, this talk will be about the large-scale total Antarctic sea ice extent, and just to get us all kind of in the mood for this after lunch, I'm starting here with an animation of daily sea ice extent from passive satellite microwave measurements. And in particular, I'm going to focus on what I see as two really intriguing enigmas about the Antarctic sea ice extent. So first, if we sum up the total sea ice extent and then look at the mean seasonal cycle, which I've plotted here, it's strikingly asymmetric. There's a long, slow wintertime advance during about 7 months of the year, and then a faster sea ice retreat during the remaining 5 months of the year. And there's a little foreshadowing of this, which I was grateful for this morning. Serena mentioned in her introduction this asymmetry of the seasonal cycle. This asymmetry is not echoed in the Arctic, where the sea ice advance seasons and retreat seasons, the red curve, orange curve, are far more equal in duration. Oops. And so the focus of the first half of this talk, the first part of this talk, is this asymmetry. Why is the seasonal cycle in Antarctic sea ice extent so asymmetric, with a slow, long advance and then a rapid retreat? And then turning to the longer term behavior, if you look at the annual mean sea ice retreat annual mean sea ice extent during every year in the satellite record, there's been a long-term expansion in the sea ice cover in the Southern Ocean. And this also, fortunately, was mentioned, I think Nathan mentioned this in the introduction of his talk this morning. Nice to get both these points brought up. So what I've plotted here is the annual mean sea ice extent in the Antarctic in blue, and then the Arctic in red. And for both, I subtracted a different constant from each, so I could put them both on the same plot. Now, the last few years have been kind of funky in the Antarctic, but to me, the really intriguing enigma here is how we had about 37 years when the sea ice was steadily advancing in the Antarctic despite a warming globe, while the Arctic sea ice was rapidly retreating. And if you look at the actual linear trend, which I've shown here during 1979 and 2015, it is not even a slow advance, but a pretty rapid one. The linear trend in the Antarctic is about half as large in magnitude as the rapid Arctic sea ice retreat. And so that'll be the focus of the second half of the talk. Why, while the globe warmed and the Arctic sea ice retreated during these 37 years or so, did the Antarctic sea ice cover expand? So here's the two halves, and or the two parts. So we'll start with the seasonal cycle. There's actually been quite a bit of work done on this. I think the one of the most leading ideas on this, and one of the original ideas, came out shortly after we started having satellite measurements in the Southern Ocean sea ice cover. And this was Arnold Gordon in 1981. And what he did is he tried to make a budget from ocean observations, a heat budget. And based on his heat budget, he said he thought that the asymmetry in the seasonal cycle in the Antarctic sea ice extent was caused by upwelling of warm, deep waters during the summer. And then that would accelerate the sea ice retreat. And then during the rest of the year, that wouldn't be happening and it would be slower. And that really became the standard textbook explanation for why the sea ice extent had this asymmetric seasonal cycle. And it was included, for example, in this kind of classic textbook, Physics of Climate, where it was presented basically as fact. This is where I was first introduced to the enigma and the for it back when I was a graduate student. More recently, a little more recently, there's been an alternative explanation that was proposed, which is that maybe the thing that drives this asymmetry in the Antarctic sea ice extent actually lies in the atmosphere and not in the ocean, specifically the so-called semi-annular oscillation of the atmospheric low pressure trough that surrounds the Antarctic continent. It undulates on twice a year. Presumably due to twice a year changes in the meridional gradient in temperature, that maybe that causes sea ice drift patterns during the summer that lead to a fast summertime sea ice retreat. And that mechanism, I think, has really been gaining traction in the field since then. There have been a handful of studies that have looked at it and tried to build on it. I think these are the two leading mechanisms for why this has happened, for why there's this asymmetry in the seasonal cycle, but there's a handful of others that have been proposed. And for those of you who are interested, there was a review paper in Reviews of Geophysics published a few years ago on all the work that's been done to address just this question, why the seasonal cycle in the Antarctic sea ice is so asymmetric. So for our work on this today, in contrast to these previous studies, well, I guess I should have said, I mean, the basis for this Enomoto and Nomura paper in 1990 is basically looking at connections they see in observational records. So they see some changes and other changes, and it looks like they go together. And Gordon et al., as I mentioned, was based on kind of a speculative explanation based on pretty uncertain observational estimates of energy budgets. So in contrast to that, what we're going to try and do is try and more systematically go through and see if we can identify step by step what could be causing this. And to start, we're going to define a measure of what we're looking at. I've defined the measure delta sub I, and it's just a measure of the asymmetry in the seasonal cycle. It just asks, how long does the sea ice advance from minimum to maximum, minus how long it retreats from maximum to minimum. So in the mean seasonal cycle, that's 208 days, minus 157 days, 51 days, about 2 months, as I mentioned. And so the first thing we looked at is, how does this vary from year to year in the satellite record? Here we're looking at a long-term mean. So that's what I've plotted here. And you can see it remains, I mean, it varies some, but it remains broadly consistent from year to year. Every year the retreat is faster than the advance, at least. And what this implies is that whatever it is that's driving this has got to be a big enough factor that it dominates over all the interannual and year-to-year variability, just the ebb and flow that happens every year in the climate system. Next, we'll turn to comprehensive global climate models. These have been mentioned a little bit in this meeting, but not very much. Cece talked a good bit about it, and I guess Serena did too, but I'll say a little bit just to make sure we're all on the same page about these things. So these models are beasts, for better or for worse. They're typically more than 1 million lines of code. And there's a bunch of them. So each of these on this axis is a different model that was developed somewhat independently at modeling centers all over the world. There are coordinated efforts that happen where all these different centers do runs under historical greenhouse gas forcing, and then they continue that on into the future under several different future greenhouse gas forcing scenarios. And that happens for the IPCC assessment reports. They come out about every 7 years, and each time there's a big coordinated effort and a whole bunch of model runs are done, and the results are made available to the community. The most recent one of these was the IPCC 6th assessment report, came out in 2021. And what we've plotted here then is what each of these models simulates for this measure, delta sub I, how asymmetric is the seasonal cycle in their simulation of the period under historical forcing, their simulation of the historical period. And the point to notice here is that the models are all broadly consistent with the observations. The observations are here in blue, and the different model results are all in black. They're not all the same, but they're all getting the right sign of the asymmetry. And the spread is, well, only medium in size. Next, we turn to the earlier generations of these models, the ones that were done for the IPC assessment reports in 2013, and before that in 2007. And we found those also got results that were broadly consistent with the observations. So what this implies is that whatever it is that's driving this asymmetry in the Southern Ocean sea ice extent has to be a fundamental enough process that through 3 generations of models developed at a couple dozen different modeling centers, you just can't get this wrong. And so our next step then, motivated by this, was to try and investigate what could be going on in an idealized model we developed that includes only what we identified as really the most salient physical processes that drive the seasonal cycle in Antarctic sea ice extent. And so we used a model. This is based on a model developed previously in my group back. Whoops, I just did something bad. Okay, I don't know what I did. But developed back in 2015, and we made some changes to the model for this. But broadly speaking, this model simulates the zonal mean surface temperature and sea ice thickness as a function of latitude and time with a seasonal cycle. This is just to give a sense of it. This is the model equations. The model simulates the sea ice thickness and the surface temperature, either the surface temperature above sea ice if it's there, or the surface temperature of an ice-free ocean mixed layer if there's no sea ice there. Manages to encompass all of that in a single variable, which is an enthalpy measure. What causes this to evolve is given by this equation here, and it's basically just conservation of energy. It says, well, any given spot in the climate system is getting heated on the one hand by solar radiation coming in from space. Some of that is getting reflected back to space with a top of atmosphere albedo alpha here. And then there's an outgoing thermal radiation to space, the infrared radiation, just because the Earth is warmer than absolute zero, and so it has to radiate. And those two are broadly the things that balance and set the temperature of the Earth. That's written here, and that is approximated as a linear function of the surface temperature, which is a classic approximation made in simple models like this. And then the third factor is horizontal heat transport in the climate system. If we didn't have that, the pole would be a lot colder than the equator than it is. The difference in temperature between the pole and the equator would be a lot bigger than it is if there weren't horizontal heat transport in the climate system. And here we're adopting a simple parameterization of that comes from a classic paper of Sellers in 1969 that says horizontal heat transport in the climate system you can parameterize as just a simple Fickian diffusion of the surface temperature. The model includes sea ice thermodynamic effects, and it ends up being, you can show the fairly standard sea ice thermodynamic effects, Sumner zero layer model you can represent, and well, it's showing up here in the different surface temperature regimes. And the model includes an ice albedo feedback right here, where the top of atmosphere albedo switches based on how warm the surface temperature is. Okay, so we take this model. Okay, a couple more things actually. The model has a insolation. So the domain of the model goes from the equator to the South Pole, and it has insolation, meaning top of atmosphere incident solar radiation, which is realistic. To get the top of atmosphere incident solar radiation, it's a geometry problem. It's pretty doable. It's a few pages if you assigned it as a homework problem for probably a graduate class. And so we've imposed that at the top of the atmosphere going from the equator to the pole. And we'll call that insolation SH sol for Southern Hemisphere insolation, just to separate it from different forcing that we'll use later. And we'll call this the full configuration of the model to distinguish it from versions we'll use later. So we run the model like this. You can run this on a laptop computer. It takes a few minutes, run it for about 100 years to get it spun up and get the mean seasonal cycle. compute the ice area from the model, and you can see the ice advancing and retreating, and then we can compute this measure, delta I. How much faster does the ice advance than retreat? And here's what we find. It does a pretty amazing job of capturing the observed asymmetry in this southern hemisphere sea ice seasonal cycle. So this is the observations, 51 days, and here's the model result. Hard to know how big an error bar you should put on this, probably pretty big, but it's amazingly close to the observations. So this is great. Our idealized model has a lot less physics than in one of these comprehensive climate models. It is still capturing this. Yes. Yes. No noise or anything like that. Yeah. That's what you meant, right? We're putting any noise in. Yeah. No, it's deterministic. And as are all the GCMs, I should clarify. Okay, so a really nice thing with a model like this is that you can turn processes on and off pretty easily to figure out what's going on in the model. And so that's the next thing we did. Now that we have this idealized model reproducing the observations, why did it do it? And so here's the model again. So we went through, first we said, I'm going to take that complicated insolation, top of atmosphere incident solar radiation. I'm going to replace it with something way simpler, just a sinusoid at every latitude. The mean of the sinusoid and the seasonal cycle amplitude will vary with respect to as a function of latitude. Next, we said, let's turn off the sea ice thermodynamic effects, and we'll call this the no ice configuration of the model. So in this situation, we'll still talk about a sea ice area as everywhere where the surface temperature is colder than the freezing point, but other than that, nothing changes in the model. So basically, it's like you have an ocean mixed layer that can get as cold as it wants. No change in albedo, no change in anything. And then lastly, we turned off horizontal heat transport, which we'll call no ice, no diff. And that's the very simplest configuration of the model. Okay, and so we try this ideal sol or southern hemisphere sol, realistic or idealized insolation, and then full model, or these three different simplifications. And we checked whether each one captures this. And maybe I should pause for a moment. You guys can all kind of imagine in your head if you can guess what the results are going to look like. We're about to look at six points. What's your guess? What is no way? With what? Well, I'm going to turn these off one at a time. So we're basically going to have 6 points. So I can do ideal sol. So which one is which one's going to lose it? So we can have two different forcings. We have three different model physics: full, no ice, or no ice, no diff. What's that? You're saying albedo is going to be the thing. I like this. So that means that when we do no ice, we won't see it anymore. And as long as we have ice, we will. Because when we do no ice, we're getting rid of the albedo effect and all the sea ice thermodynamic effects in one fell swoop. And anyone else want to boldly guess? I like that. Thank you, Mike. Well, you know. See if it's on the paper. And Ken, you can't guess either because the reviews were unblinded when the paper was published, and Ken was a reviewer. So two people in this room know. Maybe I should just show you. Okay, so here's the answer, and it turns out Mike was wrong. So in black here are the runs that have the full insolation forcing, realistic top of atmosphere insolation. In yellow are the runs that have the idealized sinusoidal insolation. And then the x-axis, the sort of columns or whatever, they're not columns, but the x-axis locations is which physics we had. Full physics, this one now no longer has the albedo effect, still gets more or less, a similar asymmetry as long as we have the realistic insolation. And this one doesn't even have horizontal heat transport, and that made almost no difference. Yeah. Totally, thank you. So the difference is that the SH sol is actual realistic top of atmosphere insolation, which is complicated, and we'll see some more figures of it later. And ideal sol is just a sinusoid at every location. So it's a sinusoid whose mean depends on latitude and whose amplitude depends on latitude. Realistically fit to the real thing, but it's just a sinusoid. No. And we'll see that in a second. Thank you. It's coming in like 3 or 4 slides. Okay, so So what this shows is that as long as we have realistic insolation, we totally capture this, even when we get rid of the albedo effect, even when we get rid of the complicated physics that causes sea ice to grow and melt, and even when we get rid of any horizontal communication. So we're still not there, but we're almost there. And so what we want to do now is take the very simplest version of the model that still gets this and try and figure out what's going on there. And this, can I get it? Yeah, this is the simplest version of the model that still gets it. So that's realistic insolation, but highly idealized physics. In that situation, the model equation looks like this. Every location is just independent. It's an independent ordinary differential equation. We're not still in PDEs. Now it's just ODEs. So this is a straight D and not a curly one. Each location, just this independent ordinary differential equation with albedo weighted insolation, although now the albedo is just a constant, and a linear bleeding term, outgoing long wave radiation. This is a simple equation. You can solve it analytically quite readily. I think the easiest way to solve this analytically is you take the forcing, you do a Fourier decomposition on it. It's annually periodic. So you just do a Fourier series, you get an annual, semi-annual harmonic, pretty much capture everything with just those two. And then you can solve analytically if you have a sinusoidal forcing and a linear ODE. The solution is just a sinusoid. So to look at this, we have been looking at the seasonal, at our measure that we've been looking at the seasonal cycle of sea ice area. And now, because we're looking at each individual location, it's nicer to look instead of the seasonal cycle and temperature at a given location. And so instead of asking what's the time between maximum and minimum sea ice area, we'll ask what's the time between maximum and minimum temperature at each location. That's what I've plotted here then. We're calling this delta sub T, is just the time period during which the temperature cools minus, whoops, whoa, gave a lot away there, minus the time period during which the temperature warms. And you can see that that measure, delta T versus time, versus latitude, I've plotted here in black. It gives a similar answer to that 51 days that we got in the observations, as long as we're looking at more or less the latitudes where the sea ice lives. So like 60 to 70 degrees south, this simple equation is simulating an asymmetry in the seasonal cycle and temperature at each location that more or less matches this asymmetry in sea ice area. Okay, so now we have what's causing this asymmetry that we're seeing, the black line. Why is this black line not at zero? And it's all about that insolation. We've got a very simple linear ordinary differential equation, but this term S, the insolation, is not simple. And here I've just plotted the seasonal cycle in top of atmosphere insolation at like 45 degrees in blue. That's almost a sinusoid. Down here at 35 degrees, it's still kind of sinusoidal, although you see some of the twice a year periodicity actually in there. As you move equatorward, once you get down to like 10 degrees, you see really strongly that there's two peaks every year around the time of your equinoxes. But then that's less relevant to this. As we move up toward the pole, once we get into high latitude regions, once we get into the Antarctic region, the insolation is characterized by this polar night, right? So here at the South Pole, half the year insolation is zero. And then we get this pretty brief and intense summer peak in insolation. So nothing like a sinusoid. And turns out, well, that's kind of all we need. So we're going to focus for this on the place where it's most extreme. So we'll look just at the South Pole. And the idea here is just, I've plotted here the insolation at the South Pole in purple, and then a sinusoidal fit to it, just the first term in a Fourier series to it in gray. And the idea here is that this thing has a long period with zero or minimal insolation, and then a brief and intense summer peak. And what that causes in terms of the temperature response is the brief and intense summer peak causes a brief and intense summertime warming. And then this long period when we're in polar night and have dim sunlight causes a long gradual winter cooling. And so this is our explanation. put a box around it. Say a little bit more about this before I conclude the first half of the talk, the first part of the talk. Let's see, first to put a kind of a finer point on this mathematically, because I just sort of hand waved the end. You can readily show that the linear response time scale in this system is just related to the heat capacity divided by your sort of bleeding rate here, B. It's 4.7 years with the parameters that we're using. Because that's substantially longer than the time scale of variability of the forcing, which is 1 year and shorter, depending on which Fourier series component you look at. You can readily show that the temperature trend would scale linearly with the departure of the insolation from its annual mean value. And that's important for this explanation to actually work, the fact that this is a long time scale. So in other words, it's the temperature trend scaling with the insolation. So a bright summer insolation causes a rapid summer warming. Next, what about the Arctic? So I mentioned in the introduction, in the Arctic, there's the asymmetry, well, the seasonal cycle is pretty much asymmetric. But in high latitudes in both hemispheres, the insolation is really similar. It's not the same because of the slowly evolving solar parameters, right? And the Earth's closest to the sun in December. So broadly speaking, you guys down here have a seasonal cycle amplitude and insolation that's like 10% smaller right now than it is in the northern hemisphere. And in about 20,000 years, that'll switch. They're not identical, but they're similar enough. When we run this model and we force it with northern hemisphere insolation rather than southern hemisphere, we get a similar answer, 43 days instead of 52 days. And that is not consistent with what we're observing. So this explanation should apply in the Arctic just like it does in the Antarctic. And what this suggests is, well, previous work said the seasonal cycle in the Arctic being symmetric is like what you'd expect. That's all simple. But that it was an enigma that we had the seasonal cycle in the Antarctic that was asymmetric with a rapid retreat. And what our results suggest is that actually the new enigma that remains to be explained is why the Arctic sea ice seasonal cycle is not similarly asymmetric to the Antarctic. And we're working on that, but we don't have an answer yet. And I'll be happy to take suggestions on that one. So to conclude the first part of this talk, the annual cycle in the Antarctic sea ice cover is asymmetric, very asymmetric, 5 months of rapid retreat, 7 months of slow advance. And our results suggest that this asymmetry arises is a direct result of how the climate responds to the top of atmosphere incident solar radiation, insolation. The fact that that's not sinusoidal, specifically the brief and intense summer peak in high latitude insolation causes a rapid sea ice retreat every summer, with then the longer period of a dim and zero sunlight in the winter causes the more gradual sea ice advance. And this simple explanation we're proposing is quite a bit different from the explanations that people have proposed in previous studies to explain this mechanism. To explain this feature. There's more details on this in a paper that we recently published with people in here, well, with Cecilia Bitz and others. Okay, I'll move on to the second part of this talk. Keep asking me questions as they come up, and then maybe I can take questions on both halves at the very end. So the second part of the talk is why did the Antarctic sea ice expand during much of the satellite record, 1979, 2015? We're going to follow the same recipe as best as we can that we did in part one of the talk. So first step is to look again at these comprehensive climate models. Now, clearly the fact that the sea ice is expanding despite a warming globe is at odds with basic physical intuition. I think like the most simple thing that everybody can probably understand is that when you warm the globe, you should melt the ice. It turns out it is similarly at odds with our comprehensive climate models. So this is a figure from a paper written by a student in my group several years ago. And this is just a histogram of the linear trend during the observational period simulated by a bunch of different climate models. Here's 0. So almost all the models are simulating a sea ice retreat. And then here's the observations in green with a sea ice advance. So comprehensive climate models don't give this. And this makes, well, now we have a different situation than we did in the first part of the talk. So in the first part of the talk, we had this interesting enigma. The climate models captured it, and our job was to explain why the climate models did so well. And now I think we have the somewhat more difficult task of trying to figure out why the climate models are essentially all failing to capture the observed feature. Now, as in the part one enigma, there's been a lot of work done previously. Oh, right. So that's the question. What physics are they getting wrong? There's been a lot of work done previously to try and explain this enigma, why the sea ice expanded and why climate models fail to capture it. One idea that's been shown up in a bunch of studies is that maybe this is just internal climate variability, just the natural ebb and flow of the climate system. But the problem with this is that based on estimates of how much internal climate variability there is, which often we get from these climate models, for this to work, you need a super unlikely realization of internal variability to be occurring in the real world. So some people get excited and they write these papers and it's like, look, a climate model can capture this, but you kind of do all the numbers and it's like, oh, that would happen like 1 in 1,000 realizations of internal variability that would work. A second idea that's got a lot of traction, especially 5 years or so ago, is that maybe the sea ice expansion was a transient response to the anthropogenically driven ozone depletion, why we have to wear so much sunscreen when we go outside here, that also was causing a change in surface winds and ultimately in sea ice expansion. There's a handful of papers written about this, but then recently, it's kind of fascinating, a paper with many of the same authors looked back into this a bit more systematically, looking with a bunch of different models and suggested it looks like it actually doesn't work. So the same team that had more or less that had proposed this really interesting idea ultimately refuted it. There's another idea that got a lot of attention about a decade ago that said this paper, Holland and Kwok, 2012, found a relationship between surface winds and sea ice drift and sea ice cover, and said maybe that would somehow explain all this. But then a paper a couple of years later said if you actually look at seasonal structure and spatial variations, it ruins it. Interestingly, this was another one where the same authors proposed the idea and then refuted it. I guess that implies if you stay tuned in a few years, we'll probably refute what we're proposing. I hope that's not going to happen, but it seems that that's a kind of a thing with this topic. But anyway, I think it's fair to say that the enigma at this point remains unresolved. And so we decided to focus on one specific possible hypothesis for this. And the idea is that maybe all the current climate models fail to simulate the Antarctic sea ice expansion due to some kind of a systematic bias in the ice drift velocity. This is a little bit related to the idea that Holland and Kwok suggested and then Holland shot down. There were reasons we thought this was a potentially promising explanation and potentially promising hypothesis, but another thing we were really drawn to about this hypothesis is that this is something that we could directly test in a climate model, as I'll detail in the next few slides. Right, and I should say that the relationship between sea ice motion and sea ice cover is not well understood and seems to be super subtle, and I'll say more about this, but there have been intriguing model biases identified in Southern Ocean surface winds, and papers have suggested maybe those are somehow related to the changes in the Antarctic sea ice cover. So we tested this in a comprehensive climate model, and the model we used was the National Center for Atmospheric Research Community Earth System Model, NCAR-CESM. Cecilia talked a little bit about this, and actually Cecilia is the one who first taught me many years ago how to use this model. We used as a control a set of simulations that have previously been run and have been made available to the community from this model, and it's 40 different simulations that all have historical greenhouse gas forcing, and then they go a little bit into the future with the greenhouse gas forcing. The only difference between them is little differences in the initial condition, and they're made just to sample what's possible with internal variability in this model. That's called LENS, the large ensemble. It's not quite an acronym. I guess it's a contraction. But lens. Those 40 simulations we use as our control. And here's a histogram of the trends in each of those 40 realizations. And you can see every single one of them gets sea ice retreat during the time period we're looking at, in contrast to the observations that give a sea ice advance. And so what we did in the model to test this hypothesis is we replaced the simulated sea ice velocity field with an estimate of the observed sea ice motion. This is an estimate that was generated by Chudy et al. It's one of several estimates that are out there, the only one that was actually publicly available. And it's based on satellite observations, satellite measurements of sea ice concentration, plus estimates of observed wind fields, reanalysis wind fields, plus buoy observations. All those are used as input to generate a gridded field of daily sea ice motion. And it turns out, as a small side note, there's clearly a massive problem in their data set, which we identified before December 1991 satellite sensor transition in the passive microwave satellite measurements. So we just ignored the time period before that and looked at 1992 to 2015 rather than 79 to 2015. It gets about the same. Observe that during that period, there's about the same observed sea ice expansion anyway. And I should say this innocent looking bullet point, just to replace the simulated sea ice motion with observed sea ice motion, it's actually no small task, right? So I mentioned these models have like more than 1 million lines of code. Shantong Sun, the student who worked on this, it took about a year to do that bullet point. So finding everywhere in the code that involves the simulated sea ice motion and trying to replace that with an observational estimate of the sea ice motion. There's some issues with how the sea ice model avoids ringing, it's ringing waves, which complicated our situation a bit. But ultimately, after a lot of work on this, we were able to get it to work. And then we can see it when it does, that the model runs, and we can see how the sea ice moves, and the sea ice actually follows the observational estimate for the ice motion. Okay, and so that's all we're changing in the model, right? We're not doing anything to heat or cool the model. We're going to do 3 realizations. We'll take 3 of the realizations, so they're indexed from 1 to 40. We took 2, 4, and 6. And those 3 realizations, we just, of the model, they all had slightly different initial conditions. And we just reran the model with pushing the ice to follow the observation. So we're messing with the momentum here. We're not doing anything to mess with heating or cooling, but we're reaching in and pushing the ice around to look like the observed sea ice motion. And I'm about to show you what the result was. And of course, I wouldn't be showing you if this hadn't worked. We do a lot of things that don't work, but it works super well. So here's what we're looking at: run 2, 4, and 6. In blue is the control runs. These are the runs with simulated sea ice motion. And in red are the 3 runs where we've specified the sea ice drift to follow an observational estimate. All 3 of the runs with observed ice motion have a sea ice expansion. So the vertical axis here is the linear trend. The dashed line is the observations. One of our 3 realizations matches very, very well with the observations. And again, all 3 of them give an ice expansion. So that's the main result of the second part of this talk. Specifying the sea ice motion in this model, we totally get ice expansion, and it can be as fast, almost approximately, as the observations. But I'll say a bit more about it. Let's see, the first thing is, it's worth emphasizing that these 3 runs are outside the range, all of them, of what the model allows when it has simulated ice motion. So it's pretty dramatic. These are the 40 runs that all have simulated ice motion, histogram of what their trends were. And these are the 3 we did where we specified the ice motion. And then we also looked at the spatial pattern. So the spatial pattern of the sea ice expansion during the observational record, it is not at all zonally uniform, as many of you may know. And what's plotted here in gray is the observed sea ice area trend as a function of longitude. You kind of see this gray line. And then the three different colors are the three simulations where we specify the sea ice motion. And the point here is, I mean, it's not a perfect match, but there is definitely like a broad consistency here in the spatial structure between our simulations and the observations. And that's in contrast to what happens when you have simulated sea ice motion here in color compared to that same gray line here where there's really no resemblance. So as in the first part of the talk, you know, it's kind of it's a zero-sum game. We feel like we address a question and we raise others. Maybe it's a negative-sum game because I feel like we raise more questions than we answer. But there's, I think that there are two big remaining questions. So in terms of what we've answered, I think this does suggest that the reason that this model, CESM, is failing to capture the observed Antarctic sea ice expansion is due to some biases in its simulated sea ice drift velocity. And similarly, then, the changes in that drift have probably played a central role in the observed ice expansion. And similarly, you know, we're speculatively hopeful that maybe there's a similar reason why all the other current climate models are failing to capture this. But two questions this raises. First, what are the models doing wrong to not get the simulated sea ice motion? So what's the actual, what's the source of the error in the models? And second, what is it about the simulated sea ice motion that's causing the sea ice not to expand? Or what is it similarly about the observed ice motion that causes that ice expansion? So I'm going to say a little bit about both these questions, but I'll warn you from up front, we don't have answers. We're actively working on them. In terms of the first one, so what are the models? Why are the models failing to get the right sea ice drift? Sea ice drift depends on a number of factors. The main ones are the surface winds, surface ocean currents, sea ice drag coefficients at the top and the bottom, and sea ice rheology. And of course, there's uncertainty in all those things. We thought kind of the most straightforward one to test was this first one, the surface winds. So the way we tested that is we went back into the code, and instead of commenting out where the model does its sea ice momentum balance to get the drift, right in there, in that calculation, the model looks at how fast the wind's blowing, and we just replace that with observational estimate with reanalysis product, ERA interim. And so the model is still simulating its full winds and everything else. It's just that the sea ice drift, when it looks up, doesn't see the model simulated winds, it sees an observational estimate. And that's the runs that we called obs wind in yellow. And what we found is that, you know, that kind of halfway, that gave half our answer, roughly speaking. So these three yellow runs, they still have sea ice retreat, but not nearly as fast as the ones with the full simulated ice motion. So I don't know. I mean, there's a spread here. It'd be nice to have more than three realizations, but I think what this broadly implies is that surface wind biases in the simulations may be partially responsible for what we're seeing in the ice drift. And by the way, there's another paper that came out not long after ours and did rather similar runs to these yellow ones and found similar results, that the ice retreat is not as fast when you fix the winds. Next, turning to that second question. Okay, so that's all we've got so far on the first question. Like maybe surface winds is biases in the surface winds is part of the issue. Turning to the second question, what are the models doing wrong in the sea ice drift? Or similarly, what is it about the observed sea ice drift that's the crux of this? It's not obvious. So what I've plotted here, this is just shading colors is how fast the sea ice is drifting equatorward. This is in midwinter, austral winter. And you can kind of see, if you look closely, the arrows is actually which way. And we're looking now at trends in the sea ice drift. This is the three realizations that we looked at that have simulated sea ice motion. This is the observed sea ice motion. I think if you just glanced at these, you wouldn't be like, oh my God, this one is definitely not like the other three. So I think it's not obvious what the model's doing wrong. And we have a lot more figures on this, but this one gives a sense of that, which is dissatisfying. And then secondly, our question was, okay, well, how does the drift actually compare with the sea ice expansion? Like, are the places where it's drifting in a particular direction expanding more or less? And so now this is the trend in sea ice drift again. Should be the same as one of those. The one on the bottom right, this is the trend in it might be actually a different season, but anyway, this is the trend in sea ice drift, and this is the trend in sea ice cover. I don't know, maybe you could try and convince yourself first. You're like, oh, look, it's blue here and it's blue here, but then like it's also blue here and it's red here. At least here, there's so much autocorrelation. There's kind of like 3 different places: blue, red, and over here that matches to blue, blue, and red. Yes. On the left, this is the trend in sea ice drift. It's a vector trend. So the color is the northward sea ice drift. So the color shows if the vector points northward, which is like this one, then it's red. And the more this vector points northward, the redder it is. So if you just want to glance at it, you got the colors. The colors have half of the information in the vectors. But if you care about the zonal, the vectors are showing the zonal too. So I guess this title just goes to the colors. Thanks for asking for that clarification. Yeah, so we don't see a clear connection. And so then next, I'll just briefly mention this. We tried messing around with a variant of the same model I talked about in the first part of this talk to see if we could figure out like what the connection is between ice motion and ice extent. I thought this was kind of a neat question because if you look at previous literature, there are a handful of papers who've said if you have an equatorward sea ice motion, some of these are Arctic, some Antarctic. If you have an equatorward sea ice motion, you had this thick pancake and you spread it out into a thin crepe, and that's a great way to get a bigger sea ice extent. But other papers say if you got an equatorward sea ice motion, you had ice in the cold Arctic, you move it into the more low latitude regions and you melt it. That's a great way to melt your ice and reduce your sea ice extent. So I feel like this has been a kind of like a carte blanche that you can sort of reach to if you're trying to explain when you see changes in ice motion and changes in ice extent. You're allowed to get it to go either way. So we wanted to sort of get to the bottom of that. And right, I've listed up here a handful of papers that did one way or the other way without really worrying about which hemisphere they were in. So we took the same idealized model basically as I showed in the first half of the talk, and we just imposed a sea ice motion. And I'll just say briefly there, we have a sort of a first chapter of the answers to this that we've published. If you want to see the details, the answer is it's not simple. Interestingly enough, it can go either way. So we found it depends on the one hand on the season when you impose the drift. On the other hand, the speed at which the drift is imposed. It turns out it's not at all linear. It also depends on the background climate, how much ice there was to start with. You can totally have situations where turning the equatorward drift up causes the ice extent to go down. You can have it cause it to go up. It's a simple enough model. You can come up with physical explanations, and I think rather rigorously show that you are explaining what the model is doing for most of this behavior. Some really intriguing behavior. It turns out that the wintertime sea ice extent is more sensitive to the summertime sea ice motion than it is to the wintertime sea ice motion. We got a lot of complicated results here. We didn't get anything really clean and simple. That's why it's in, like, I mean, Geophysical Research Letter is a great paper, but a journal, but we probably would have gotten it even fancier if we had some simple explanation. Nothing simple happened there, and we're still working on it and still trying to find something simple. So good time to conclude the second part of this talk. Okay, so Antarctic sea ice cover has been expanding for most of the satellite record, and most climate models, including CESM, don't capture this observed expansion. I should say CESM, it's not just Cecilia and I who use it. I think it's probably the most used climate model in the US, if not everywhere. You think it's the most, what's the most used climate model? CSM, you think? Yeah. I hope we're not having like American myopism. We found that this problem in CSM could be fixed if we manually corrected the sea ice drift velocity. Putting in an observed estimate of the sea ice drift velocity caused the model to suddenly capture that Antarctic sea ice expansion. And we don't really understand why, and we're still working on that. So I think this suggests that sea ice drift has probably played a central role in the observed expansion, and that an improved representation of sea ice motion is crucial then based on this to accurately simulate the historical period and by extension to make accurate projections of the future. So put up the conclusions of both halves, and thank you.
Thank you, Ian. Any questions?
Alex Fraser with a question. So in the first half, you tested it out on the Arctic. What happens if you test out part 2 in the Arctic and prescribe the drift in the Arctic?
That's a great question. So, yes, thanks for asking that. Okay. So the models are similarly biased in the two hemispheres, and we have it's this paper actually. Okay. This is my time to conclude. I did well, right? I was a little ahead of schedule. Thank you. So the point in this paper was that this is a little background before I answer that. As of like 2012, the GCMs were simulating way too slow in Arctic sea ice retreat. And by the time it was like 2015 or 16, GCMs were often capturing the Arctic sea ice retreat. And the point of this paper isn't actually like this one figure that I showed, but the point of this paper we wrote in 2017. So the reason they were capturing it is because they were getting too much global warming during the observational period, during the sea ice retreat period. They weren't getting too much global warming during the 20th century overall, but during 79 until like 2015, they had too much global warming. And it has to do with a number of factors you can probably explain. But it turns out that it sure looks like that is what was allowing them to get as fast a sea ice retreat as they got. And if instead you ask, how much sea ice retreat do you get per degree of global warming? It's a long literature that on using that as a measure. It might be a little more robust as a measure among the models than using a time trend. The models have more or less kept their bias the same for the last 3 generations. They simulate way too little Arctic sea ice retreat, way too much Antarctic sea ice retreat. The biases in the two hemispheres are very similar to each other. So when we went in and we simulated the sea ice motion, we felt like we had 2 chances of getting an interesting story, right? Either the Arctic or the Antarctic, because we simulated it in both over the global domain. And nothing interesting happened in the Arctic. It exacerbated the problem slightly. So when we use the observed sea ice motion in the Arctic, it causes the sea ice retreat to be slightly slower in the model. And we would have been excited if it caused it to be faster. But maybe that also speaks to how tempted we are to follow the easiest path, because there's like a 50-50 chance it could go either way. And if it goes that way, I'd be up here telling you, oh, it looks like this is the key thing in the Arctic. I'm not sure. I'm too cynical. But that's what happened in the Arctic. It made the sea ice retreat a little slower, and it exacerbated the bias compared to the observations.
Thanks, Ian. It's Ken Golden. Is there any data or conjectured behavior of the evolution of Antarctic sea ice volume?
Yeah, and there are probably, what? So there are probably some people in this room who can answer this better. I think there's a big issue when we want to go over this multi-decadal time period to try and get it, right? I'd really love to see what is the Antarctic sea ice volume done during 79 and 2015. And I guess you'd use geomass. How do you say it? G-I-O-M-A-S? No, the global instead of polar. The biomass has a sibling from the same group with a G in the front. It's gotten a lot less work. It's way less detailed. It's not nearly as cool as and I think G is for global and P is for polar, which is interesting because polar could have been either one, but that has an estimate, but I don't feel like people go to that the way they do to the biomass estimate for Arctic. CC. Oh, does anyone have I mean, how much can we say about the changes in volume over? That gets tricky that it's not that much of the time period we're looking at. But with a model, it would be interesting. And that was the thing. Like, I mean, we can totally see what happens in the volume when we like do the observed ice motion compared to the simulated ice motion, but we're not sure what to compare it to, which I think is what you were getting at with your question, right?
But also just, volume is, I mean, thickness is hard to measure.
Yeah.
And so, in other words, is the ice, is it just expanding out and getting thinner? So there's really not that much volume increase? Or is the thickness decreasing faster than the expansion of wind blowing it out or whatever? Or
if we knew that, we would know so much more, right? It would be a
That'd be
lot
great.
cooler if we had more measurements of the thickness. Because then we'd, yeah, I agree all the way.
Wish we knew. Did you look at the ocean? Because CESM's ocean is biased pretty too stable. So
The stratification is too stable.
the stratification is too high, and so it doesn't mix deeply enough. It's biased, too extensive in the wintertime. Did any of these things improve as well?
I don't remember. We don't have any of that in our supporting information. The student who did this, Shantong, cares a whole lot more about the ocean than the ice, and we definitely looked at it and talked about it a bit. I think he was really hoping there'd be a sort of a companion piece of it that was something really interesting happening in the ocean. I don't know that we looked at this specifically, or I don't remember what we found if we did.
I could always thought was bias contributing to coordinate.
So you're referring to your own paper from, right, that with this 2011, was it? Right, about yeah. Yeah, and this was that mechanism. This was basically that ozone-driven mechanism. I kind of felt like Kurtman and you have a paper related to this. We can talk about it afterwards.
Ian, we have one more question.
Oh, thank you, Ian. Rob Masson. I wonder if we're missing a process here. When my very first encounter with Antarctic sea ice was in the mid-1980s, I was on a cruise with Steve Ackley and others, and a striking thing was that as the ship went into the marginal ice zone, it was a forming sea ice cover. There was frazzle ice formation under a long period swell regime. It was cold sea surface temperatures. And the ice edge was expanding at a rate of knots to the north, but there were no winds that were blowing it from the south. It was purely a thermodynamic process set up by the wave environments. So I wonder if that's something that's missing from, it's an enigma in itself in terms of the ice advance around Antarctica. And it could well be, a regional thing in the Weddell Sea and the Ross Sea, for instance, but not necessarily elsewhere.
I like that, but I would say, I mean, you're talking about observing the mean seasonal cycle, and I would say if I were to put that anywhere in this simple talk, I would put that in the first half. And I will say that our explanation for that mean seasonal cycle didn't have any motion in it. So it was just a thermodynamic expansion and freezing and melting. In terms of the second part, I think it's okay if the mean seasonal cycle is overwhelmingly driven by a story that doesn't need ice motion. I don't think that's inconsistent with the second, because here we're asking what's causing the long-term trend. So I think what we'd have to do is have you observe how that differed from one year to the next over, well, 37 years or shorter. Does that seem reasonable?
I'm just wondering how you could include such a process in the models, Ian, and whether it would be possible.
I don't, it's there that the ice, when the water gets cold, the ice forms, but it's a bit crude, right? The ice forms at 50 centimeters thick. CC might have something more to say about this. It does not still use the H naught of 50 centimeters. CIC doesn't. When you form new Fraenzel ice, CSM doesn't still use that Hibbeler parameter.
Let's all thank Ian again.